Hey Level 3s, and welcome back to 3.4 Atomic Structure and Bonding and Thermochemistry. This is Lesson 15, Part B. So we were just talking about entropy of the system before, and now we're going to talk about entropy of the surroundings. So entropy of the surroundings is actually relatively straightforward. It all depends on the enthalpy of the reaction. So whether the reaction is exothermic or endothermic. And it's always the same answer if it's exothermic, and it's always the same answer if it's endothermic. So with an exothermic reaction, we know that heat is released to the surroundings. So that means that the surrounding particles gain kinetic energy, therefore they move faster, therefore there's greater disorder, and the entropy of the surroundings increases. So for every exothermic reaction, entropy of the surroundings goes up. For all endothermic reactions, entropy of the surroundings goes down. And the reason why is because heat is absorbed during an endothermic reaction. This means that the surrounding particles have less kinetic energy, so they move slower, so there is less disorder and entropy decreases. So this is the same every time. So these kind of paragraphs are really worth memorizing or making sure you understand. You don't really need to memorize. You just need to realize that if heat is being released, then particles speed up, disorder goes up, and if heat is being absorbed, surrounding particles slow down, less disorder. So you just need to understand that. So when we predict whether a reaction is spontaneous or not, we now need to look at both the entropy of the system, which is those equations that we were doing earlier. So you look at the equation, you look at the states, and you look at the number of particles and decide if entropy of the system is going up or down. And we also need to look at entropy of the surroundings, and the entropy of the surroundings is to do with the enthalpy, so whether it's exothermic and endothermic. Now, a really useful tidbit to know is the fact that if both the system and the surroundings gain entropy, then the reaction is spontaneous. So if both the system and the surroundings gain entropy, then the reaction is spontaneous. So if the system gains entropy, so the positive entropy, so if it goes from liquid to gas, or if there are more particles being produced in the products, that's a positive system. And surroundings, the only way to have surroundings gain entropy is if it's exothermic. So if you have positive entropy of the system and an exothermic reaction, then the reaction will always be spontaneous. So there has to be an easier way of kind of remembering what situations with enthalpy and entropy will cause a spontaneous reaction. Now, what this slide is, this is Gibbs free energy and the equation. Now, you do not have to do this equation. I repeat, you do not have to do this equation. However, this is a really useful tool to help you understand the situations in which we can have spontaneous and non-spontaneous reactions. It's really important you understand that Gibbs free energy must be negative for a spontaneous reaction. So Gibbs free energy must be negative for a spontaneous reaction. So let me go through and show you what I mean about this equation. Now, there is another factor to this that I'm not going into with you at level 3, and that's this temperature thing. And it does actually matter about the temperature, but we're going to assume all these situations are at the same temperature so we can ignore it. Okay, so if we're trying to work out, because your question in NCA will ask you whether the reaction is spontaneous or not given the information. Now, a lot of us teachers really hate the fact that Gibbs free energy is not in the curriculum. This is not technically in the curriculum, but it's the best way of explaining this stuff. So let me go through and I'll talk about the situation. So we're ignoring the T, so just cross that out. So effectively we're doing H minus S to see if we can get a negative value, because a negative value for G means spontaneous. So let's have a look. H, enthalpy change, S, entropy change. So if the reaction is exothermic and there's a positive entropy, if we're doing H minus S, if you look here, it doesn't matter the size of either, you always produce a negative value. So therefore, these reactions will always be spontaneous. So let's say H was -4, because we said it had to be negative enthalpy. And we said entropy was positive, so we made it's H minus S, so we're saying +6. -4 minus 6 equals -10, because a minus and a minus makes another minus. And then if we have -6 instead, so we made enthalpy bigger this time, bigger than entropy, -6 minus 4, it still equals -10. So it doesn't matter the size of these two numbers of enthalpy or entropy, you will always get a spontaneous reaction. And so that's what we were saying before, because when we think of enthalpy, remember, if it's exothermic, that means the surroundings are increasing in entropy because heat is being released to the surrounding particles. They're moving faster, they've got more kinetic energy, so greater disorder, greater entropy. And if it's endothermic, then the surroundings are always going to lose entropy because energy is being absorbed, the particles are moving slower with less kinetic energy, so less disorder, less entropy. So we already know that if you have positive entropy of surroundings and positive entropy of system, that it's going to be spontaneous. And this is me just mathematically showing you that that is the case. So what situation is never possible? And the situation that is never possible is to have an endothermic reaction that has a negative entropy. Okay, an endothermic reaction with a negative entropy is never able to happen. And let me tell you why. So if we have positive values for our enthalpy, and the equation is H minus S, and S is negative here. So +4 minus a minus is a positive. So you get +10, means it's not spontaneous. If this was the bigger number, +6 minus -4 is still, they add, so you end up with a positive value again, and therefore this is never ever possible. So you can't have an endothermic reaction with a decrease in entropy. It is not energetically favorable, so they never occur. So what if you have two positives, endo and a positive entropy? Is this possible? It's only possible in one situation, and that's if one of these values is bigger. And in this case, the value that has to be bigger is the entropy. So if our enthalpy is +4 and then we minus off +6, you'll get a negative value and it will be spontaneous. If we flipped them round and made the enthalpy the larger value, you can see +6 minus +4 equals +2, and it's not possible. So the only way to get a spontaneous reaction if both enthalpy and entropy are positive is if the entropy is bigger. And we would say in this instance that the reaction was entropy driven because entropy is having the bigger effect. Now, I do apologize here. I might have to write up the second line at the bottom. It's just tipped off so you can't really see. So let me go through it. What if we've got exo and a negative entropy? So if we know it's H minus S, so H is -4 minus -6. Well, the two minuses here become a positive, and you end up with a value of +2, which is not spontaneous. The line that's underneath that I'm just going to move up here is what if we made the enthalpy bigger? So -6 minus -4, well, you end up with a -2, which is spontaneous. So this time the H had to be bigger, and so we say that this is enthalpy driven. So it is possible for one situation, if both enthalpy is negative and entropy is negative, to have a spontaneous reaction, and that's if enthalpy is bigger or having a greater effect. And so it is possible for an endothermic reaction with a positive entropy change to happen, but only if the entropy has the greater effect. So I know this is a lot to take in, but it's literally purely maths, and that's what I'm trying to show you here, that if you do H minus S and you get a negative value, you could plug in any numbers you want in your exam to check it. That'll tell you if the reaction is positive, like as in if it's possible to be spontaneous. And to be spontaneous, the G must be negative. I hope that makes sense. Any questions to me on Teams? So here's an example now. Now I'm really hoping that you guys were able to find a balloon at home because this is a really useful activity. So what I'd love you to do is to get a balloon, put it on your lips and pull. Put it on top of your lips. And when you pull that balloon, so you stretch your balloon, you'll feel that your lip heats up. And so this must be pulling the balloon. If it's releasing heat to my lip, pulling the balloon must be exothermic. And we know that if a reaction is exothermic in one direction, it has to be endothermic in the other. So if I pull the balloon and it gets hot, so exothermic, then releasing the balloon, contracting it, must be endothermic. Okay, so that's from our observations, we can draw those conclusions, right? So I'll say that again, stretching the balloon, I feel my lip get hot, which means that energy is being released, which means stretching the balloon is exothermic. So if I let it go, okay, then that must mean relaxing the balloon is endothermic, okay? So if that's the case, now we need to think, well, let's from observation work out whether stretching the balloon is spontaneous or not. Now you probably know that for me to stretch this balloon, I'm having to put in a fair amount of energy here, so it's not likely that that's the spontaneous route, but if I let it go, it naturally contracts. And I'll do that again. So if I stretch the balloon and then let it go, it naturally contracts, telling us that the spontaneous reaction here is contracting. So contracting the balloon is spontaneous, okay, because it just happens. It'll happen without me doing anything, okay? But we know that stretching the balloon is exothermic and contracting it is endothermic, which means in this example, the spontaneous reaction is actually endothermic, which often doesn't happen. Most spontaneous reactions, from that table that you just saw before, most spontaneous reactions are actually exothermic. So how can it be possible that this contracting of the balloon, which is endothermic, actually be the spontaneous reaction? And it has to be to do with the entropy. So what is going on in the entropy of it? So when we look at what's actually happening, if you look at these pictures down here, when we stretch the balloon, all of the polymers inside the balloon become very ordered and they lay on top of each other. They become very ordered. And when you let it go, let it contract, they all become all disordered and tangled again. And we know that an increase in disorder is an increase in entropy. So actually the contraction of the balloon is an increase in entropy, which is why even though it's endothermic, it is still possible. And so the only way that we can have an endothermic reaction, so a positive H and a positive S produce a negative G, is if the fact that the entropy is having the greater value here, or the greater input. So a balloon is a really good way of explaining to you how it is possible to have an endothermic reaction be spontaneous, but the only way for it to be spontaneous is if this entropy is having a much greater effect. So the massive disorder gained outweighs that endothermic aspect of this reaction. I hope that made sense. So the last thing to finish part B video, and I'm going to have to come on and do a part C, is here's a nice quick 2-minute YouTube video on entropy if you ever have time to have a look at it. It's nice, short, and it's pretty good. So there's the link there. Okay team, I'll see you shortly for part C.